So,
For much of my career, I've had an agenda of wanting to understand the whole range of appropriate issues in training of flexible classes of functions of many variables. Single hidden layer neural nets and deep neural nets are an example of such. The types of questions that we want to explore include questions of how well functions can be approximated by these objects, how well from a finite amount of data can they be estimated, and how well can you compute the parameters in terms of computational complexity. When it comes to the parameter computation, because of the multimodality of the functions that you would like to maximize, gradient descent methods can be problematic, and it's advisable to use stochastic methods. Associated with that, it's natural to think, instead of least squares type estimators, to think of posterior sampling. So to get there, let's start off by thinking we have data. Each x, and sometimes we'll put an underscore to remind that it's a vector. Each x is a d-dimensional d variables. And we have observation indices I from 1 to n is the sample size. And we might have a response variable yi that I'll take to be a scalar output. So to get us oriented, the posteriors you might want to think about might arise from a mixture model, where under an assumption of independence, you have the product of the sums of components of the mixture. So for instance, you can think here of the case that these are Gaussians, and the thetas could be the locations of the Gaussians. And the weights could be non-negative and sum to 1, and that's a Gaussian mixture model. Okay? And this component here is your likelihood, and this part is your prior. For instance, each of the thetas could be independent and from some normal prior. As we'll see, though you could parameterize the weights of combination, I'll be talking about a flexibility of freedom of the number of components, and it will be acceptable to fix those weights in particular ways that I will discuss. In a regression setting, the likelihood if the responses y are Gaussian with conditional means that are modeled, then you have this Gaussian likelihood structure. But it turns out, even if the y's are not Gaussian in their errors around a true function, if you sample from a posterior that pretended as if they were Gaussian, it's still statistically accurate from a frequentist standpoint. And I will be taking advantage of the exponential of a sum of squares of error structure. Now, as I said, we're interested in a variety of questions. One question is, how reasonable is it to use such models, be they Gaussian mixtures or neural net mixtures? For instance, in the neural net case, this could be a hyperbolic tangent. That's one natural choice. I will make that choice specifically later. Or it could be any bounded increasing sigmoid, or it could be a ReLU. Would be the types of functions that one might use. And here you were in a Gaussian location. The theta plays the role of a shift. Here, this phi, it has a scalar input, and you get it by a linear combination of the input variables, perhaps with a shift or offset b. So we're interested first in what can we say about approximation. So I began to think about this in the late 80s. Lee Jones and I had conversations leading to recognition of an important class of functions. This class of functions are those that are natural for the class of basis functions you're using. So let's assume that our basis functions are bounded, like the hyperbolic tangent is, and the variation of a function f with respect to this class, also called the atomic norm, would be the smallest v, such that if you take f over v, it can be approximated arbitrarily accurately by convex combinations from phi. So f over v would be in the closure of the convex hole of phi. And then from either a simple sampling idea, you can see that the approximation error can be controlled by that variation squared over m. But from the standpoint of getting towards estimation and computation, it's also very useful that there is a simplicity of type of approximation that one can take. So you can iterate for little m up to big M, where your next approximation comes from a relaxed modification of the previous one by bringing in a new term. If phi is closed under sign change, you can just use plus. If you you use pluses or minus. This would be variation 1, because you'd be taking a convex combination. To allow for variation v, we would do this. And here the idea is, at each step, you seek out a single theta. You don't try to estimate or approximate, all the thetas at once. This is important ultimately in computation because there really are a lot of symmetries that get in the way of rapid mixing of Markov chains for these things. You have all the m factorial permutations. But once you choose to do it in a greedy fashion, the restricted sampling has more of a chance to be rapidly mixing. Now, the alpha here, if f is actually in this convex hole of v times phi, then the alpha could be 1 over m. And then you could keep running it. You could keep running m as long as you want. If you have a final capital M in mind, it's okay to start smaller and use that for little m up to big M. This has the advantage that each alpha is small, and this is going to be important also in our rapid mixing result when it comes to sampling. But you can also, if f does not have good variation with respect to phi, you could choose some v, and you could ask for the projection of f onto the ball of radius v, and then you would use that v, and you would use an alpha of something like less than 1 and of order 2 over m, and then you would achieve error in approximation of the projection with another factor of 2 there. These are all results that have a history back in the 1990s and work by Lee Jones and myself and Lee, Barton, and Williamson and many other authors. Later, a lot of it is summarized in a paper with Ron DeVore and a couple of other colleagues. So the point is, in getting the theta, you would choose it at each step so that when you take this form, from the approximation standpoint, having already gotten a previous approximation, you can think about that as a residual function. And you are asking to come as close as you can to that residual by a certain multiple of the functions in this class. But this is still a difficult optimization for nonlinear phi, and that's why there's more to do. So that's a brief summary of what I want to say about approximation, but it leads in naturally to estimation.
Equal to RD, or so does this approximation theory depend on what you choose for?
No, it doesn't really. What I've written here doesn't need this. All it needs is that you have an inner product space and that the individual phis have a norm of 1 in that space. If the norm is something bigger, then it can be incorporated here. But for the statistical purposes, the particular Hilbert space norm will be L2 with respect to the probability measure that the x's are going to be drawn from. Also, when it comes to verifying variation results, one idea that's similar to what we were just hearing about is to think of the Fourier representation of f. And a Fourier condition can be used to show that a function has bounded variation with respect to this class. And then you might want to be much more particular about what thetas you allow and what's the ranges of the x's. It becomes handy, for instance, to constrain x to either be in a ball, either a cube or a Euclidean ball. Now we come to estimation. So we mimic the structure. We are going to come up with an estimate which is of the form of a linear combination of the phis. Oh, and I should say at this point, what I said here is kind of oriented towards the regression-like setting. In work with Jonathan Lee and others, when you're dealing with likelihood modeling by mixtures of Gaussians or other families, it could be handy to look at pullback approximation error, and it's of similar order. There's a similar story. So there's actually a focus towards the neural nets, but these mixtures are going to crop up. They crop up in 3 ways. One, because you might be interested in things like normal mixtures or logistic regression mixtures. Another, you can think of this as mixing, a probabilistic mixture. And a third will be when we come to the computation. Yes?
So what do you mean with bounded variation? Sum of absolute value of the coefficient?
So, yes. So what you're saying is VF is the infimum of V such that F is in the closure of the convex hole of F over V is in the closure of the convex hole of V. So you could say, consider approximators for which the sums of the opposite values of the coefficients remains not more than V. Then, as long as the function can be approximated arbitrarily well, in that class, then the variation is not more than V, and you have this bound. Okay, so now for estimation, there's two ways to go. There's more papers written about the greedy least squares, but one can do likewise and have what I'll call a greedy Bayes. In greedy least squares, you're doing the same thing. It's just that the measure for the L2 norm is with respect to the empirical distribution. And since Y has error, you are in the case where you would want to be projecting to that class, and so you would use these types of alphas or a fixed final value. And again, what you could say one thing, which is that you come close to the minimum sums of squares that you could have in that convex hole as M gets larger and larger, but you're interested more not just in how close you get to Y, but in how well you estimate F. But another way to go, you could call it greedy Bayes. So you would think again in the greedy setting, but now instead of the minimizer of this squared error incrementally, you would take the posterior mean. Richard, this is what I was asking about. To me, it's even if theta is the parameter I'm working with, the function I want the posterior mean of is something like this. I think that deserves attention. Now, when you look at this structure, you can expand the square, and you see you have the part that comes from the residual squared. You have the part that comes from the inner product, and you have a part that comes from the square of this part. The square of this part has the v squared alpha squared in it, and as it's going to turn out, the appropriate size of that v squared alpha squared makes that not an important term. It's really only the cross product term that matters, and accordingly, a greedy pseudo-posterior to work with would replace this by just V alpha over 2 sigma squared summation I equals 1 to n residual I times phi of xi theta. The same goes true for this minimization. Indeed, in the original Lee-Jones greedy algorithm, he chose the thetas to optimize such inner product with residuals. Doing so produces another factor of 2 in the bounds compared to using squared error, but it simplifies the structure of either the minimization or the sampling. There were questions?
Integral is phi of x comma theta m, or is this the nth component, or?
This is, I'm asking for the nth component.
So the integral is, maybe I can't read the
So
subscript.
the whole nth component would become a mean of these using your posterior.
So is there subscript m missing in the integral of the theta, or?
Yes, but here you can think of it this way, that you're fixing m for the moment, and you're focusing your attention on the theta m that you want to introduce. You could call it theta for now.
And the phi is sort of the density you're trying to estimate, no? So
The phi is, like in the neural net case, my arctangent.
so you,
And I'm trying to, maybe with a fixed offset, and I want to, instead of dealing with the nonlinear optimization problem of finding that coefficient of the arctangent, instead I will take a posterior mean. Now, if I do that posterior mean by a Monte Carlo, I make repeated draws from this to approximate this integral, and then I average the result, which still leaves me in the class of linear combinations of these things.
You're not trying to learn the theta here, but...
I don't care about theta. It's rare that we care about parameters. We care about functions that are parameterized by the parameters. It's all data can ever teach us about. Parameters index the things of interest to us. If they have a nice structure, like a Logconcavity, that's helpful, but it's not the thing we care about. Okay, so if we do these things, now we come, so far, this would be for arbitrary data. Now, when we deal with it statistically, we should comment that not only does the fact that you use squared error in your likelihood not matter critically, knowing the right sigma does not matter critically. What you were dealing with is kind of a different gain, overall gain in this annealing-like sampling interpretation. But now suppose that input-outputs come IID, and this assumption is only for this segment, only for this little part of the board. They come IID from some joint distribution on x's and y's, where the distribution on x is constrained to the x's that are used in defining these variations. And the mean of y given x is f, and the variance is either homogeneously sigma squared or bounded by a sigma squared. And the norms used on this board are the L2 norms with respect to the P of x. Then what one would expect is that the overall error of an f hat fitting f would be analyzed by splitting into two parts an analysis of how close an approximation fm is to f, and then how much additional estimation squared error you have from your finite sample. And so this you would control under the variation condition by a v squared over m. And the additional estimation error, and this is related to comments I made yesterday, come in one of two varieties, depending on metric entropies of the class of capital phi that you're dealing with. And in particular, let's suppose that capital phi is now, a ridge function with phi fixed and smooth. Then you kind of have two different ways of covering. One is to kind of pepper the individual y covering, because that's what controls, as in the previous talk, the additional estimation error or metric entropies. And you could cover the theta 1s through theta m's to, you have d coordinates, so this is the total number of real numbers that you describe, each to an accuracy of 1 over square root of n or 1 over n. And so that would be a number of bits in a metric entropy cover or description length bound on the risk. But if you have L1 control on the thetas, then you can again use these same type of approximation and cover ideas, and it leads to a worse rate with n, but a better rate, well, it kind of depends on the size of m, but certainly a better rate with dimension. So from this perspective, you could allow much larger dimension. And then how do you find m? In practice, don't do what I'm about to say. In practice, you'd have some penalized likelihood criterion, like a minimum description length, and you would choose the m that optimizes that criterion. But according to these bounds, the best m is of the order of the square root of the sample size. Yes?
The second one, right?
Yes, there is, because it turns out that you can cover the whole Blumen convex hole as well, without having to. You still need to have made M big enough for this part to be of the same order. Yes? You had another, yeah.
Was this now for the least squares estimated these bounds, or is this for the posterior mean as well?
The papers are all published for the least squares. For greedy Bayes, now that you will see I have a result for it, those papers need to be written. But I believe that it'll all go through. Yes?
So you're using metric entropy of these convex hulls?
Yes.
Smooth, the phi's are smooth functions of theta and pieces, finite dimension.
Yes.
It shouldn't be RD.
Right. If the metric entropy of this class phi is like that of a finite dimensional class of some metric dimension d, then that's the d you would use over there, no matter what the ambient dimension was.
Do you know the Theta bounds?
Not necessarily. My mind hasn't been on those things for a long time. I've been mostly thinking about
Are
computation.
these phi's all uniformly bounded? I mean, like, if you want the Bayes estimator to work, you want the Hellinger distance to be compatible with the L2 distance in your random design regression.
If you care about theta, but if you don't care about theta and you care about these functions, then it isn't critical.
Well, but you still want the prior model. I mean, if you want to actually prove something for the posterior mean, you still want the Hellinger distance and your prediction risk to be the same. And for this, you'll need
There
uniform.
are two different ways of studying the accuracy of Bayes procedures. One is to literally do what I'm saying, and then you do need the separation properties that I first worked on for consistency results in the late 80s and von der Waart extended to get rates. But already in that work, you can see there's another way to use Bayes, where you take a Cesaro average across sample sizes of the Bayes procedures. And for that purpose, you don't need the uniformly consistent tests or other separation properties. You only need cover properties, and life is much easier.
So that's not the posterior mean, though, then, no?
Right, so you would need to, according to that, you would do this not for some final n, but for each n from 1 to that final n, and you would take Cesaro averages of those. Let's get to the interesting part that I spent most of my career thinking about. I feel like I'm finally getting somewhere. And let's take note that I started at about 10:10. So what we want to do is we want to sample from a distribution with density p theta proportional to e to the alpha summation and what I was calling residual I, let's just call it Ri. And let's think in particular about the hyperbolic tangent. You could have the freedom of a bias. That's a scalar parameter. You could just say, we're going to try each b in a grid of values. So I will focus attention on the thetas. This p theta is proportional to this, and I'm going to be thinking about a Gaussian prior, though there could be reason to use other priors. Now, in order to sample, there are various strategies for what to do. You could set up some Markov chain Monte Carlo, with a fixed transition rule. And there will be at time t a distribution pt that results. And the interest is in how does pt approach p. So there will be a path of distributions in any of these strategies. You could try to be explicit about the path pt that you want. So you could prescribe a path, for instance, an annealing path, taking you from the prior to the posterior. And if you could track that, that would be nice. And because this is a workshop on statistical estimation and deep learning in PDEs, I'm going to turn that around and say PDEs are one way to approach this matter of how to track the distributions. And this page is just for that purpose of fitting it in the bigger picture. I'm not actually going to use what I'm going to write here, but so creating a path. One way would be to use a stochastic differential. So you could say, in continuous time, there would be some drift dt, and you could, in general, have dispersions that are state-dependent and time-dependent, but let's just write sigma dB. Where here, time is continuous or discretized. And this is worth writing because Fokker and Planck in physics and Kolmogorov in mathematics worked out the PDE that expresses how PT evolves for such stochastic diffusions. So there is an evolution PDE. Rather than writing it, I'm going to actually come around to it indirectly. Let's mention, as an example, the case that the drift could be not changing with time and just sigma squared over 2 gradient of the log of p theta. And then that's sometimes called a Langevin diffusion. That's a time inhomogeneous transition rule for which p is the invariant distribution. This is, in essence, a stochastic gradient scheme. And I think it is entirely possible that for the p that I've defined over there and alpha in the range that I'm talking about here, that it's rapidly mixing. I've been trying and been unable to prove it, but I think that it's within the realm of possibility. Another way to go would be an ordinary differential. Where you say d theta is some, you have a velocity field, drift tilde, of t, time-varying velocity field, and you let theta move accordingly. Now, there is the so-called continuity equation that says how PT evolves. It evolves according to this PDE. So you take that drift times p, it's a vector, you take its divergence, the sum of its first derivatives, I think there's a minus sign, and that expresses how PT evolves. Now, to get back to Kolmogorov-Fokker-Planck, if you do the natural thing and relate these drifts to make the general drift here, let me do it in a different color so the board doesn't look too cluttered. You make drift T equal a drift tilde of T plus half sigma squared gradient log PT. Then that's a stochastic differential that has the same evolution as does PT, or vice versa. You could, from this, write out, plugging that in, you get the Kolmogorov-Fokker-Planck equation. What that means is in the Kolmogorov-Fokker-Planck, it always separates into two parts. If you have a positive sigma, there is a canceling part of drift that would be associated with not changing the distribution, and a part of the drift that changes the distribution. So at the core, if you can solve this equation for the deterministic velocity field drift tilde, then for a given path, like an annealing path for PT, then you would track that distribution exactly in continuous time or approximately in discretized time. Okay, so that's what I want to say at the overlap with PDEs. I know that there's been recent literature. Google and ResearchGate tells me every time a paper is referenced. The last couple of years, there's been a big turn-up of referencing of my earlier work from the PDE community, because they are saying that if the driving function of a PDE or the coefficient functions of a PDE are of the class that I introduced and that I was talking about there earlier, that then the solution remains in that class, and so they're seeking solutions to PDEs by neural nets. To me, that's nice, but a little bit backwards, because I don't know how to train neural nets. For me, I want to solve a PDE so I know how to train a neural net. Okay, so let's come to the matter of what I propose to do in taking advantage of that structure. So I want to now take specific use of the tangent hyperbolic function for single hidden layer neural net, where the phi x theta is tan hyperbolic of x dot theta with perhaps an offset b. But this is not essential to what I want to say. It's important for its general applicability, but I'm going to leave it off for the discussion. So now we have a mixture trick. The mixture trick is to consider a logistic mixture so that's a number between 0 and 1, a scaling of the logit function or of the hyperbolic tangent. But I use alpha Ri, a minus sign, and then the complementary weight. With e to the plus Ri. Now, you look at it, the Taylor expansion of its log for small alpha. And what you find is that this is equal to e to the alpha Ri, tan hyperbolic of xi dot theta plus order alpha squared with constant bounds on the coefficient of the alpha squared. So the object that we are taking products of here are themselves approximately mixtures. And accordingly, we can think, and sometimes I will write the subscript alpha to remind ourselves of the alpha dependence. And it comes from the prior times the product of these expressions. With, of course, a normalization. Now, recognizing, so this is a mixture. The K can either be just 1 or 2, or I'm going to parameterize it by a Z that's plus or minus 1. And so this is the sum over Z vectors, Z1 to Zn, in minus 1, 1, to the n of P alpha theta Z1 through Zn equals P0 theta, product I equals 1 to n, e to the Zi, theta dot xi plus alpha Ri, divided by e to the minus theta dot xi plus e to the plus theta dot xi, e to the minus c alpha. So this is now a mixture model representation where what's nice is that for each labelings of the coordinates, this is Logconcave in theta. So it's strongly unimodal. It's of the form of exponential of minus the convex function of theta. Alpha, in order that this be close to what we wanted, we what matters, because you're going to be summing these up, you have n of them. So remember that our optimal alpha, 1 over m, was of the order of 1 over square root of n. So when I square it, it's order 1 over n. And so I have a 1 over n error on each of the n terms. So I have a bounded error of this distribution used as a surrogate for this one. So that if I can sample from this one, then by rejection sampling, I can sample from that one.
The error is still of constant order, no? So it's not small.
Right, but for sampling, what you want for reasonable rejection sampling rapidity is to have a constant bound on the ratio.
So the target is Logconcave up to an additive perturbation that is bounded.
Yes.
So in terms of the mixing time of the Langevin, you will still get an exponential hardness in the additive perturbation.
Right, well, instead I sample from the Logconcave mixture. Then I can, if I can produce repeatedly samples from that Logconcave mixture, then as an end step, I can apply rejection sampling for the original target. The same is true if instead I wanted a square of error, it had also an order alpha squared term, so I can actually sample from the greedy posterior with the square of error by rejection sampling, obtaining as my pilot draws the result of a chain sampling from this Logconcave mixture. Yes?
Does the big O term also scale in Ri? I was curious.
Yes, it would. Yes.
In your hydrogen sampling step, how do you avoid exponential dependence on dimension?
Because the constant doesn't depend on dimension here.
Even after
Well, it depends, okay? To be more careful. If you remember, I wrote out what M should be, and it did have dependence upon D, okay? You could choose to be statistically a little bit suboptimal, use this M instead of the statistically optimal one, and now your risk will still be okay with respect to N. It'll be a little bit worse in terms of its dimension dependence. This is nice. It's nice to know what are the computational accuracy trade-offs. We may have to work harder to compute the best estimators that we can produce bounds for. If we work with alphas that are this, then things are nicer here, but the rate might be a little bit worse statistically. Okay, but just because you have a mixture of Logconcave does not end the sampling problem. So any Gaussian mixture is a mixture of Logconcave, but Gaussian humps can be very far from each other. So now what we need to take advantage of is the fact that the alpha is small, and this produces not too much freedom of separation of these Gaussian components. So to say a little bit more, once you have this joint distribution, you have the various associated objects. For instance, so let me write, this is Logconcave.
So Andrew, our next talk is in 10 minutes, so we can wrap up in 3 or 4 minutes.
Yes, I can.
The next talk is online, so.
All right. So this is an integral of such. So there are means for rapid computation of such integrals. Integral is strictly Logconcave, and there's a lot of literature about that, by sampling. So you now have access to various objects. For instance, this conditional, by taking the ratio, it's Logconcave. And you also have access to the distribution of the z's given theta, and it makes them independent, where these are just logistic with these log-odds. So there are then two natural Gibbs strategies, Gibbs samplers. One Gibbs strategy you could call the Gibbs cycling. You add a theta, and you get your z's by independent draws, conditionally given theta, from these Bernoullis, symmetric Bernoullis. Not symmetric, I mean, plus minus one value Bernoullis. Then, given the z's, you get your next theta by Logconcave sampling. A sampling that's analogous to a logistic regression sampling. The other natural Gibbs sampler is coordinate Gibbs sampling. For instance, on the z's, you pick a random I from 1 to n, and you look at how this thing that you can evaluate where that zi is either +1 or -1. And so the conditional distribution for that zi given the others is proportional to those two values. And you make a draw from that conditional distribution of that coordinate given the others. And then you repeat that. That's coordinate Gibbs sampling. Now, the study of the mixing property of such chains, so I've been advised to not, I'd love to talk some more, but I won't write more, I'll talk more. There is very recent work by Chen and Eldon, appeared on the archive 1 month ago. Actually, less than 1 month ago. So I've been rapidly working to incorporate what I learned from it. It gives a general framework for looking at various types of Markov chains to explore the Poincare constants or log Sobolev constants. What one needs to be able to do if you have a distribution is you need to, well, the Poincare constant is an infimum over test functions g of the ratios of expected squares of g of theta minus g theta prime, or g of z minus g of z prime. That expected square using the joint distribution under stationarity divided by the variance of g itself. But in these chains, you can identify what they call a stochastic localization, a martingale. That martingale is simply you draw a random ordering, k1 through kn, and you look at the distribution on the z's given the values of the first z's in that order, t going from 1, and you stop at n minus 1. This is provides a martingale that enables you to write that Poincare ratio, that Poincare constant, as a product of ratios, and in each ratio, they give tools for its analysis. Now, what happens is in that setting, I could look at the special case first of alpha equals 0. When alpha equals 0, when you have your conditioning on, say, t of these values of z, you still have the other factors, but they sum out. And so those conditional distributions are Logconcave, and you use a Braskamp-Leib inequality on that ratio for the alpha equals 0 case. And then for alpha different from 0, you do a Taylor expansion on the ratio that arises in that factor of the Poincare constant in the martingale analysis. And fortunately, the order alpha equals, first order derivative respect to alpha is 0. And so it's an order alpha squared thing that remains. And the resulting Poincare constant can be bounded. And that bound takes a form that involves, I'll just write one thing. A constant that arises is the operator norm of a matrix A, where Aij is the absolute value of the inner products between xi and xj. And so, for example, if the xi's are all unit norm and have 0 inner product, they're orthogonal to each other, as is possible if the dimension is bigger than the sample size, then that operator norm is 1, and you have rapid mixing. But even if the operator norm is bigger than 1, if it's bounded, you have quantification of the mixing time. So this provides, I believe, the first steps of results for rapid mixing in these neural nets, which enables you to train single hidden layer neural nets with prescribed accuracy. Thank you.